Welcome to Logical Verification 2020-2021, Chapter 13, Section 2, the second part of the construction of the real numbers. In the last video, we've looked at the definition of Cauchy sequences, and now we're continuing this to construct the real numbers. So we have this picture here of convergence sequences being the one that get arbitrarily close to a limit, which we already need to have as an object, and Cauchy sequences, which allow us to omit the limit and just talk about the sequence itself. And Cauchy sequences are the ones that we can already apply to rational numbers to describe sequences that converge to something that is not a real number, that is not a rational number, such as the square root of 2. And very similar to how we constructed the integers from pairs of natural numbers and the rationals from fractions of integers, we'll now construct the real numbers from Cauchy sequences of rational numbers. So in Lean, we can define Cauchy sequences exactly as I've drawn on the whiteboard. The definition looks exactly like what I've shown you, so there should be no surprises here. And then we define the type of Cauchy sequences as the subtype of all sequences that are Cauchy sequences. Okay, so far so good. We'll need to define an equivalence relation on those Cauchy sequences that we will later on use to define the quotient of those Cauchy sequences, and this quotient will then be the real numbers. Okay, so we need something that tells us when do two Cauchy sequences converge against the same limit. Again, we don't have the limit yet, because we do not have the real numbers yet. So in general, we cannot take the limit of a Cauchy sequence yet. So we'll need to define it in terms of the sequence itself without talking about the limit. And one very simple way to do this is to say that the difference of the sequences converges to zero. Okay, and this allows us to define a setoid on the Cauchy sequences using this equivalence relation here. That is exactly what I've drawn. Maybe I should rewrite this here. It is exactly this one here, this notion of convergence here, which says that for every epsilon greater 0, there is an index after which the difference between two sequences and the limit, which is 0, is smaller than epsilon. So we say that, maybe here. Right, so we say that two sequences, xn and yn, are equivalent if and only if the difference converges against 0, in this sense that we've discussed before. Okay, and that's why this slightly large formula comes from. Okay, now we need to prove that this is indeed an equivalence relation, that it is reflexive, symmetric, and transitive. Reflexivity and symmetry are fairly straightforward. However, transitivity shows us a very common proof technique used when we prove things about epsilons, namely that what situation that we have here? So we want to show transitivity, which means we know that the difference between the first two sequences converges against 0, and the difference between the second two sequences, so like in the second and the third one, converges against 0. And now we need to show that the difference between the first and the third sequence converges against 0. So maybe I should draw a picture. So what we have here is we have 3 sequences. We have one sequence, we have a second sequence, and we have a, it's not what I wanted to picture, and then we have a, it wasn't the color that I want to use, and then we have a second sequence, and then we have a third sequence here. And what we want to have is, we want something that is, right, so we want to be within epsilon of 0. So like, say this is 0 here, right, so this here is 0. And we want to be within epsilon of 0. So we have an, right, so we have this epsilon here, and we want to be within an epsilon of 0. We want to be in this strip here. And now the way we do this is we budget this epsilon into 2 parts. So we need to be within 1. So we're allowed to make an error of epsilon. So we are making an error. So we'll budget this to make an error of epsilon half between the first 2 sequences, and another error of epsilon half between the second and the third sequence. And then what happens is, when we take the distance between this one and this one, it will be less than epsilon half plus epsilon half, which gets us, which is below epsilon. And this is exactly what we do here. So when we show transitivity, we need to show that for every epsilon greater 0, there exists an n such that for all indices after that big N, the difference between the first and the third sequence, so between f and h, is less than epsilon, and we'll split this epsilon into 2 parts, epsilon half for the difference between f and g, and then epsilon half for the difference between g and h. This comes up fairly often, so remember, this is a good technique. Okay, so, right, so we take our assumptions and set epsilon for hfg to epsilon half, and also for hgh to epsilon half. Okay, what we then get is the h big N1, which tells us that after all indices after big N1, the difference between f and g is less than epsilon half, and similar for all indices greater than n2, the difference between g and h is less than epsilon half, which means that after the maximum of both indices, the combined error is less than epsilon half plus epsilon half, which is, well, at most epsilon. Okay, and this is, the rest of the proof really just combines those in this way, using appropriate lemmas from the library. Okay, so now we know how the equivalence relation looks like on Cauchy sequences. And we can start defining the operations on the Cauchy sequences. So let us first define some constant numbers like 0 and 1, and also for every rational number we can already say what the Cauchy sequence corresponding to a rational number should be, and that is the constant sequence, which of course also converges against this rational number, so this seems like a good choice. So we define the constant Cauchy sequence for every rational number, which completely ignores the index, and for every index in the sequence returns the same rational number, and this is a Cauchy sequence by a straightforward proof. Okay, next we define addition. So the addition of 2 Cauchy sequences is the addition of each of the components. do component-wise addition. And so the proof here is omitted, but it uses a very, hint is use something similar to epsilon half. So you might need to use epsilon quarter here, actually, I think, because the Cauchy definition of Cauchy sequence is a bit idiosyncratic here. So there are a lot of ways to define Cauchy sequences and conversions that differ by only very small details. So, for example, it does not matter in any way whatsoever if you have here less than epsilon or less or equal than epsilon. And there are lots of other variations. So instead of for all epsilon greater 0, there exists an n, such that this here you could also say that for all epsilon greater 0, there exists an n, such that for all n greater than n, the difference between xn and xn, n is less or equal epsilon. So this is all equivalent to Cauchy sequence. And another one is that for all epsilon greater 0, there exists an n such that for all n greater n and for all m greater n, xn minus xm is less than epsilon. So there are lots of variations on this. Maybe you can try proving some of them to be equivalent. Maybe some definitions like this are more convenient to prove that the addition of Cauchy sequences is again a Cauchy sequence. Yeah. So this is not the only possible choice of definition of Cauchy sequence here. Okay, anyhow, so once we find addition of Cauchy sequences, the one thing that we still need to prove to be able to lift it to the quotient afterwards is that this definition of addition is compatible with the equivalence relation that we had on Cauchy sequences. And this is proof, again, uses the same approach of dividing up the epsilon into two parts and then combining it afterwards so that the errors add up to epsilon. And the rest between it is really just reasoning about the sum of the errors. And yes, that's very similar to the other proof. Right. And once we have this, we can finally lift it to reals. So by lifting to the quotients, and the quotient of the Cauchy sequences is the real numbers. And here, well, we get 0, which is the lifted version of the constant 0 sequence. We get a 1, which is the lifting of the constant 1 sequence. Well, we also get a function that actually goes for every rational number to the real. We don't have notation for this yet. So how do you write this? So not only do we have it for 0 and 1, we actually get it for every rational number. And we can also define the addition of real numbers by lifting the operation on the Cauchy sequences to the quotient, which is possible because of the lemma that we proved earlier, that the addition is compatible with the equivalence relation that we introduced. Okay, so this is one way to construct the real numbers. It's using Cauchy sequences is convenient because proofs such as here that because the definitions that we can define the addition of Cauchy sequences are fairly straightforward. We can, mainly because the addition of two Cauchy sequences is just the component-wise addition of the sequences. And similar for the multiplication of two Cauchy sequences is just the component-wise multiplication. So this makes Cauchy sequences a very convenient way to define real numbers, but there are other constructions of the real numbers that are different and sometimes not as convenient. So maybe the most other important one are so-called Dedekind cuts. In a certain sense, you can think of it as the difference between Cauchy sequences being a completion with regards to sequences, so we want to add limits for all convergent sequences as defined by the distance. And Dedekind cuts complete this by the order. So here with the Cauchy sequences, we have Cauchy sequences, so like sequences that would converge if they are real numbers. And with the Dedekind cuts, we represent the reals instead as intervals of rational numbers. So well, as half-open intervals, essentially. So as sets of rational numbers that are essentially of the form all rational numbers being less than a real number. And then you can also define the addition on them by taking all the additions of the two sets that you get here. However, multiplication is a bit more difficult. But I mean, you could do the same construction here in Lean as well. You would first define a subtype of sets of rational numbers that have that. So of course, you cannot define them this way. You cannot consider the subtype of all sets such that there exists a real number, such that the set has this form, because we don't have the real numbers yet. So you need to define a different description of this kind of set, which only talks about rational numbers. This is not hard. And then you can define these sets are then called Dedekind cuts. So you define a subtype, the subtype of Dedekind cuts, and then you get the real numbers without a quotient construction. And the third one would be to consider decimal expansions of the real numbers. Decimal expansions of binary, so decimal expansions, or right, and we had this example at the beginning where it was the square root of 2 is 141, and so on. And you can also define the real numbers by considering such infinite sequences of decimals, or I mean, you can also do this in binary or in hex if you want. This is also somewhat inconvenient because it's hard to define addition on